This is Chapter 2 of the Basic Chemistry series. This chapter is on the structure of atoms. All matter is composed of atoms. Atoms are the smallest particle of an element that retains its identity in a chemical reaction. Atom comes from the Greek word atomos, meaning indivisible. An atom has three parts: a proton, being positive, a neutron that has no charge, and an electron that is negative. The proton and the neutron are found in the center of the atom, a place called the nucleus. The electrons orbit the nucleus. Elements are the alphabet to the language of molecules. To make molecules, you must have elements. Elements are made of atoms. While atoms may have different weights and organization, they are all built in the same way. Atoms always have as many electrons as protons. Atoms usually have about as many neutrons as protons. Adding a proton makes a new kind of atom. Adding a neutron makes an isotope of that same atom, a heavier version of that atom. You can see hydrogen has one proton and one electron, which would demonstrate the term usually have about as many neutrons as protons. Helium has two protons, two electrons, and two neutrons. Carbon has 6 protons, 6 electrons, and 6 neutrons. Elements are the building blocks of all matter. The periodic table is a list of all the elements that can build matter. It's a little like the alphabet of chemistry. The periodic table tells us several things. The difference between atoms and elements are similar to a word that is either singular or plural. An atom is singular or an individual piece. An element is a type of atom. Many atoms can be of the same element. A gold bar has many atoms, but is one element assuming it is pure. So if this was a stack of gold bars, all this in here, this is an element gold, which obviously have several atoms. Down here, these little circles would represent an atom. So each one of these would be an individual atom, but they're all the same element. A mixture is two or more substances that are combined physically but not chemically. They are made of many different kinds of particles that can usually be separated. Examples of mixtures: a mixture that lacks uniformity in composition is called heterogeneous. Examples of this would be a rock. A rock is made up of minerals in different proportions. Another example of a heterogeneous mixture would be vinegar and oil. A mixture with vinegar and oil would not be the same throughout the composition. Another type of mixture is called a homogeneous mixture. A homogeneous mixture means the solution has the same composition throughout the solution. Examples of this would be when salt is dissolved in water, or someone makes a cup of coffee or a cup of tea. Substances can be classified as elements or compounds. A compound is a substance that contains two or more elements chemically combined in a fixed position. When the elements sodium and chlorine combine chemically to form sodium chloride, there is a change in composition and a change in properties. Sodium chloride, commonly known as table salt, is a white solid. The chlorine atom by itself is a pale yellow poisonous gas. An atom is the smallest particle into which an element can be divided and still be the same element. Atoms are building blocks of matter. They make up everything around you. Individual atoms are too small to be seen. To give an idea how small an atom is, 1 penny is made up of about 2 times 10 to the 22nd atoms. An atom is the smallest unit of an element. It consists of a central nucleus surrounded by one or more electrons. In the center there is a proton and a neutron, and on the outside there's an electron that is in orbit called a shell. The nucleus is a central part of an atom. It's composed of protons and neutrons and contains most of the atom's mass. A proton is a positively charged particle and is found within the atom's nucleus. A neutron is an uncharged particle and also found within the atom's nucleus. An electron is a negatively charged particle located in the shells that surround the atom's nucleus. All elements must contain identically charged electrons. We know this from the cathode experiment from J.J. Thomson in the late 19th century. Atoms are neutral, so there must be a positive particle in the atom to balance out the negative charge from the electron. Electrons have so little mass that the atom must contain other particles to account for most of the mass. The modern atomic thought began with John Dalton. Dalton used experimental methods to transform Democritus' ideas of atoms into scientific theory. Dalton studied the ratios in which elements combined, and the results were Dalton's atomic theory. In 1808, John Dalton proposed atomic theory. Dalton's theory explained several laws known at the time, which were the law of conservation of matter, the law of definite proportions, and the law of multiple proportions. The following is Dalton's atomic theory of 1808. Number 1, elements are made of tiny particles called atoms. Number 2, atoms of a given element are identical. Number 3, atoms of different elements differ from each other in some fundamental way. Number 4, atoms of one element can join with atoms of another element to form compounds. A given compound is always made of the same elements combined in the same way. This explains the law of multiple proportions and the law of definite composition. Number 5, atoms are indivisible in a chemical reaction. Chemical reactions change how atoms are grouped together. This explains the law of conservation of matter. Let's go into a brief history of the atom to illustrate how the atom developed over time. In 1904, Thomson developed a model of an atom that was made up of electrons scattered unevenly within an elastic sphere surrounded by a soup of positive charges to balance out the electron's charge. This model was called the plum pudding model, like plums surrounded by pudding. Some years before this proposed model, Thomson discovered the subatomic electron, saying they are negatively charged subatomic particles. Thomson performed the experiment using a sealed glass tube with gases in it. He passed an electric current through the tube, and the result was a cathode ray. Another contributor to the electron was U.S. physicist Robert Millikan, 1868 to 1953. Millikan carried out experiments to find the quantity of the charge carried out by the electron. He calculated the mass of the electron that is very similar to the accepted mass given today. Eugene Goldstein, 1850 to 1930, observed in 1886 that in a cathode ray tube there were rays going the opposite direction. He concluded that these were positively charged particles. Protons are positively charged subatomic particles. Each proton has a mass about 1,840 times greater than an electron. In 1932, English physicist James Chadwick, 1891 to 1974, confirmed the existence of another subatomic particle. Neutrons are subatomic particles with no charge, but a mass nearly equal to a proton. Rutherford's gold foil experiment. This experiment changed the prevailing thought of the structure of an atom. Because of this experiment, Rutherford concluded that most of the alpha particles pass through because the atom is mostly empty space, and the reason that some of the particles were deflected were due to the concentration of the positive charges in the atom, which is now known today as the nucleus. The nucleus makes a very small portion of the structure of an atom. If I really wanted to give a proportional description of the atom. I couldn't even do it on this tablet that I have here. A good analogy would be if a baseball was a nucleus, the size of the atom in the electron field would be about the size of the baseball stadium. Niels Bohr came up with a model of the atom that we now know today as the Bohr model. Bohr postulated that fixed energies related to the orbit. Electrons cannot exist between orbits. The higher the energy level, the further it is away from the nucleus. And an atom with a maximum number of electrons in the outermost orbital energy level is stable or unreactive. So essentially what Bohr said was there were fixed energy levels for electrons and that electrons could not exist in between energy levels. Let me come out here. If this was energy level 1, energy level 2, energy level 3, that an electron couldn't exist in between energy level 1 and 2. It would have to be within here, one of these energy levels. And the higher the energy level, the further it would be away from the nucleus. Say this is the nucleus. And so energy level 1 would be the lowest energy level. And then after that, it would be energy level 2, then energy level 3. And if the outermost orbital energy level was filled, then it would be stable. We'll get more into that later. So between about 460 BC and 370 BC, Democritus came up with the idea that an atom was made up of a small particle. More than 2,000 years later, in 1808, John Dalton described these small particles as being different from one another, which we now know as an element. In 1886, Goldstein discovered the proton, which is a subatomic particle within the atom. In 1897, J.J. Thomson discovered the electron, which is a subatomic particle. In 1904, Thomson proposed a model of the atom, which was described as the plum pudding model, where the outside had slightly positive charges and the inside had negatively charged particles. In 1909, Goldstein proposed that the atom was made up mostly of empty space, and Millikan defined the atomic weight and charge of the electron. And in 1913, Bohr proposed energy levels of the atom. And in 1932, Chadwick discovered the neutron, which was a subatomic particle. So concluding the atom is indeed the smallest indivisible particle that can still have an elemental identity. Dalton described atoms as having different types, which we now know as an element. Goldstein described a positive subatomic particle, which we now know as a proton. Thomson described a negatively charged subatomic particle, which we now know as an electron. And he also recognized some relationship between the positive and negative charges between the proton and electron. There's a vast amount of empty space within an atom. And in 1913, Bohr described different energy levels that the electron orbits. And in 1932, Chadwick described a neutrally charged subatomic particle, which we now know as the neutron. In its entirety, we have the model of an atom, which has a positively charged proton, which is in the middle, a neutrally charged neutron, which is in the middle. These combined are the nucleus of an atom. The electron is negatively charged and follows an orbit around the nucleus, which can only be in defined orbital levels from the Bohr model. The periodic table is very important in chemistry. It was created by Mendeleev. The periodic table arranges the elements according to their atomic number and reveals patterns among the elements' properties. Elements in each column share similar properties. The periodic table shows all known elements in the universe and organizes the elements by chemical properties. Atomic number. This refers to how many protons an atom of that element has. No two elements have the same number of protons. Atomic mass. Atomic mass refers to the weight of an atom. It's derived by adding the number of the protons with the number of neutrons. This cartoon is a helium atom. Valence electrons are the electrons in the outer energy level of an atom. These are the electrons that transfer or share when an atom is bonded together. The horizontal rows are called periods in a periodic table. Periods equal rows. They go from left to right. What do elements in each row have in common? The same number of electron shells. Every element in period 1, the first row, has one shell of its electrons, hydrogen and helium. All the elements in period 2 have two shells for their electrons, and it continues like this all the way down the table. So what that's saying is, in the first row with hydrogen and helium, this row right here, so it has one shell which the electrons would orbit. And period 2, which would be this row, it would have two shells the electrons would orbit. And period 3, which would be right here, would have three shells which the electrons would orbit. The columns on a periodic table are called groups or families. These groups or families have the same number of valence electrons, or electrons in the outer shell. So this column would be column 1, so it would have one valence electron. This column is a second column, so it would have two valence electrons. Going all the way to the other side, this would be group 18, and this would have 8 valence electrons. If you notice, this skips from group 2 to group 13, going from 1 valence electron to 2 valence electrons to 3 valence electrons. We jump from group 2 to group 13. Here's another style of periodic table where this would be group 1 or 1A. This would be group 2 or group 2A. And jumping over here, this would be group 13 or group 3A. Let's look at a bigger picture of this table so you can see what I'm talking about. So right here you can see that it's 1A, 2A, 3A, and so on. So those would directly correspond to valence shell electrons. Let's go over what we already know about an atom. We know that in the center there's a positively charged proton. There's a neutron that is neutral, and together these make the nucleus. The electron is on the outer part of the atom, and it follows a path that is called a shell. We said that the elements that are horizontal on the periodic table are periods, where every element in that period will have the same number of shells. Period 1 has one shell, period 2 has two shells, period 3 has three shells. We describe the groups on the periodic table as having elements that all have the same number of valence electrons, or the same number of electrons in the outermost shell. So what is a valence electron or the outermost shell? The outermost shell, or these shells, the outermost part of the atom, are called valence electrons. So when we say all of the elements in group 1 have one valence electron, that would mean that they have one electron in the outermost shell. So period 1, there's only one shell, so there would be one. For period 2, there are two shells, so there would be one electron on the outermost shell. For period 3, there would be three shells, so there would be one valence electron in the outermost shell. Going to group 2, or column 2, all the elements in this column would have two electrons in the outermost shell, or two electrons in the valence shell. So starting at period 2, there would be two shells, and the outermost shell, there would be two valence electrons. So that would be this element right here. And moving down to period 3, there would be three shells, so there would be two electrons in the outermost shell, which would be the valence electrons, and that would be this element. The elements of a periodic table can be divided into three main categories: metals, nonmetals, and metalloids. Properties of metals: good conductors of heat and electricity. They're shiny. They are ductile, meaning they can be stretched into a thin wire. They're malleable, meaning they can be pounded into thin sheets. A chemical property of metal is its reaction with water, which results in corrosion. Properties of nonmetals: they're poor conductors of heat and electricity. They're not ductile or malleable. They are brittle and break easily. Nonmetals are usually dull. Many nonmetals are gases. Properties of metalloids: metalloids have properties of both metals and nonmetals. Metalloids are solids that can be shiny or dull. Metalloids conduct heat and electricity better than nonmetals, but not as good as metals. Metalloids are ductile and malleable. Let's talk a little bit about how atoms are built and how they are all built the same way. What makes the electron configuration of an atom stable? Energy and stability play an important role in determining how electrons are configured in an atom. There are 3 rules to consider when writing an electron configuration of an element. An electron configuration describes the ways in which electrons are arranged in various orbitals around the nucleus of an atom. The first rule is the off-ball principle. According to the off-ball principle, electrons occupy the orbitals of lowest energy first. In the off-ball diagram, each box represents an atomic orbital. For now, I'll just use the Bohr diagram to describe what this means. So if we have the Bohr diagram, start filling in the electrons from the lowest energy right here, which would be this orbital on the Bohr diagram, and we would fill the electrons of the atom from the lowest energy up to the highest. So on the off-ball principle diagram, it would go from the bottom to the top. And on the Bohr diagram, it would go from the inside out. The off-ball diagram shows relative energy levels of various atomic orbitals. Orbitals of greater energy are at the higher part of the diagram. Another rule is the Pauling exclusion principle. According to the Pauling exclusion principle, an atomic orbital may describe at most 2 electrons. So using the Bohr model again, if this was an orbital, at most 2 electrons could occupy this orbital, so there could not be 3. And using the box from the off-ball diagram, we had 1s, here was the box. The most we could put in this box, this orbital, would be 2, couldn't put 3. To occupy the same orbital, 2 electrons must have opposite spins. That is, the electron spins must be paired. What that means is, when we have the orbital 1s, the electrons must have opposite spins, and we do that by having kind of like half arrows, where one is pointing down and one is pointing up. Spin is a quantum mechanic property of an electron and may be thought of as clockwise or counterclockwise. So if an electron was in an orbit, one would have to spin this way, and the other electron would have to spin the other way. Using a box from the off-ball diagram, we show this by writing an arrow down, kind of like a half arrow down, and another half arrow up. A vertical arrow indicates an electron in its direction of spin. This is using regular arrows. So an orbital containing paired electrons is written as one arrow going up and one arrow going down. I've also seen them where the arrows, they had half arrows too. The third rule for electron configuration is called Huns Rule. According to Huns Rule, electrons occupy orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. 3 electrons would occupy 3 orbitals of equal energy as followed below. So what this is saying is, once you have orbitals of the same energy level, they're degenerate. And what Huns' rule is saying is the electrons need to fill the orbitals with the same spin one box at a time. And after the last one is filled the same spin, we go back to the first one and start pairing them up with opposite spins. like this. So going back to this slide, that's where these boxes are coming from. So from this, there's already 2 energy levels that have been filled, which would be 1s and 2s, 2p. So these are already filled. 3 electrons would occupy 3 orbitals of equal energy. Electrons then occupy each orbital so that their spin is paired up with the first electron in the orbital. Looking at this diagram, you can see how the electrons are filled with each element. Starting off with hydrogen, we have 1 electron, and then moving to helium, we would have 2 electrons, so they would be paired up. Lithium would then add another electron, which would go in the second orbital. And jumping to carbon, you can see how with the addition of each electron, it's placed in orbitals of the same energy, or degenerate orbitals, where it has the same spin. Moving from nitrogen to oxygen demonstrates how all the degenerate orbitals are filled with the same spin, and then when we add another electron, we come back and start pairing up the orbitals. So looking at the orbit filling diagram of oxygen, we can see that the 1s orbital has 2 electrons of opposite spin, which is right here. The 2s orbital also has 2 electrons of opposite spin, which is right here. Each of the 3 2p orbitals has 1 electron. The remaining electron now pairs with an electron occupying one of the 2p orbitals. So this is filled up. So the 1s orbital is filled. The 2s orbital is filled. 1 electron goes in each orbit of the same energy, and oxygen has 8 electrons, so it would come back and pair up, occupying one of the 2p orbitals. So in the electron configuration, these are orbitals. The number in front of the orbital type describes the energy, and the superscript describes how many electrons are in the orbital. So if there is 1 electron, it would be 1s1. If there was 2 electrons, it would be 1s2, or 1s with a superscript. 1 electron in the second orbital of the 2s would be 2s1. 2 electrons would be 2s2. 1 electron in the 2p orbital would be 2p1. 2 would be 2p2. 3 would be 2p3. 4 would be 2p4. And this would be the electron configuration for oxygen. So let's summarize what we know. An electron configuration is the arrangement of electrons of an atom in its ground state into various orbitals around the nucleus of an atom. The off-ball principle, the rule that electrons occupy orbitals of the lowest energy first. So what that's saying is we start at the bottom of the energy and we go up to the highest energy when we fill the electron orbitals. The Pauling exclusion principle says that an atomic orbital may describe at most 2 electrons, each with opposite spins. So each orbital, this would be 1s, this would be 2s, this would be 2p. Each orbital can occupy at most 2 electrons, so we would put 1 here. They have to be opposite spins, so we would have to put another half arrow in the opposite direction to indicate an opposite spin. And we would start from the bottom to the top. Spin is a quantum mechanic property of an electron. It may be thought of as clockwise or counterclockwise. So 1 arrow going up would indicate one direction, and 1 arrow going down would indicate another direction, or clockwise and counterclockwise. Huns Rule. Electrons occupying orbitals of the same energy in a way that makes the number of electrons with the same spin direction as large as possible. So what that's saying is when we go to the 2p orbital, we would fill this up with electrons going in the same direction because they're the same energy first to make it as large as possible, and then come back and fill the rest with opposite spins. So when we make an electron configuration, we use the off-ball principle, starting out at the lowest energy, We use the Pauling exclusion principle, saying that we have to pair up each orbital with opposite spins. And we use Huns Rule, which says that electrons occupying orbitals of the same energy level must be filled in such a way that makes orbitals with the same spin as large as possible. This concludes Chapter 2.